Thank you very much. I'm really excited to be here today. I've been doing ODSC events for ages now, it seems. I think the first one I did was back in 2015, somewhere around there anyway. So it's real exciting to be here with folks. I would love it if people would start putting some stuff in the comments. Maybe tell me whether you prefer Claude or ChatGPT when it comes to a large language model to work with, and you can't answer both. So if there are folks on there, shout into the void here and make sure that you guys can hear me and that everything's working. So let's see if we can get some comments coming in. While we're waiting for that, let me just introduce myself a little bit. My name's Greg Michelson. All right, Alex, I see ChatGPT. Yeah, I pay for that $200 a month plan, and I use it all the time. It knows me so well. It also knows my food preferences because I use it for recipes all the time. Turns out ChatGPT is a pretty good cook. So one fun project you can do with ChatGPT is you can ask it to tell you about yourself, and it's kind of alarming the things that it knows about you. So everybody, that's your homework when you get done here. Go on ChatGPT and say, "Hey, tell me about myself," and see see what it tells you. It gets some stuff wrong, but it knows a surprising amount. All right, another vote from Chris about ChatGPT. That's good. All right, so my name's Greg Michelson. Oh, we got a Claude vote. It's a tight race. I was the chief customer officer at Data Robot back a few years ago, and in 2021 joined a company called Zerve helped found a company called Zerve. And what we do is we're building a data focused agentic coding environment, a development environment that allows you to use Python and R and SQL to build data pipelines in a really robust way. Because we looked out at the landscape of tooling that was available. So I don't know if you folks know about Data Robot. Data Robot, we were focused on automated machine learning. And so automated machine learning is, the pitch was even your grandma can build predictive models. Let the computer do it for you, kind of thing. And so Data Robot was very much democratizing data science, and everyone can be a data scientist and all that kind of thing. And the way that I got involved with our other two co-founders is that they reached out to me on Zerve and on LinkedIn and said, "Hey, we're doing this thing called Zerve, and we don't really understand your marketing there at Data Robot." Of course, by that time I'd left at Data Robot, and so they were Philly, the CEO, actually reached out and said, "We don't get it. Like, we need you to explain it to us because we don't think that everybody can be a data scientist, and we don't think that this automated machine learning thing can actually work." And I reached out back to him. It was a cold LinkedIn message, and I said, "Hey, I don't think so either." In fact, we had a huge team of management consultants there at Data Robot, whose only job it was to help people figure out what they needed machine learning for in the first place. And so, yeah, that's very real. And so we started building. Hey, Daniel, nice to see you. Let's everybody that's with us. This was sort of billed as kind of a code along type event. So we're going to be working in Zerve today. And Zerve is free to use. It's a development environment. I'm going to hop in and show you about it a little bit. But if everyone will go to Zerve.ai, let me go ahead and share my screen. You can sign up for a free account, and then you can follow along today. And where are you, window? There we go. So if everyone went to Zerve.ai, you can sign up for a free account, and that'll give you plenty of credits for today. You'll be able to follow along and do everything that we're doing if you just click sign up here. I'm already logged in. And the problem that we're going to try to be solving today is a cloud cost optimization problem. So folks may or may not know how cloud compute works. There are different types of instances that you can pay for when you're working with the cloud providers. Some are like reserved instances where you pay in advance. Some are sort of spot instances where you just use them kind of on demand. There are a couple different kinds of instances that you can buy, and depending on the workload that you have, there probably should be a mix of those different types of cloud resources that you use when you're actually trying to orchestrate your workflows. And the goal there would be to not only minimize cost, but also maximize reliability. So, you can always just buy the most expensive type of instance and have it there, whether you have the workload for it or not. Or you could always just buy when you need it, and if something's not available, then you're taking a hit in terms of reliability. So you may not be able to get the compute that you need if you don't have some preserved. So I wanted to use our time today to do some agentic coding. So we're going to use the Zerve agent to kind of take a stab at this problem. And so I've got a little prompt here that I'm going to put in here. I'm going to say, build a cloud cost optimization simulator using synthetic data and generate a realistic workload, model on-demand, reserved, and spot capacity with the cost-risk trade-offs, and then search for the lowest cost policy that still meets demand and reliability constraints. And then I'm asking it to be sure to visualize the different proposed scenarios and pick out the best one. So we're going to do basically a simulation here. And I don't have any, since we don't have real data for the cloud compute, we are going to go ahead and just use synthetic data to make that happen. So while it's thinking here, you can see the agent chat going on over here. The interesting difference between, say, like a Claude Code or a ChatGPT and something like Zerve is that Zerve has full visibility into the context of the problem that you're trying to solve. And so Claude Code can't see your data. It can't see the results that have come when you execute the code in your environment. It can't kind of like iteratively respond to what's going on. All it can do is write the code based on the context that you give it. Well, the upside of having an agent integrated with your development environment is that it gives you that capability to see the analysis live and for the agent to be able to react to what's coming out of the analysis and adjust its behavior accordingly. And so you can see the agent has written a couple of cells here. And so it's doing some work here. And it's you can see this is a very familiar kind of notebook type style view. And we've already started to generate some code, which we'll go and look at here in a minute. But I want to give you kind of the lay of the land in terms of where everything is located inside of Zerve. And so if you're following along, if you've signed up for Zerve and you've got your account, then you've got the free tier gives you 5 credits per month, or 50 credits per month, sorry, that you can use. And those credits are consumed when the agent does its work and also for compute. So those two things eat up your credits, and we'll be able to see exactly how many credits we used in this project today. But down here is the plan. So the first thing that Zerve comes up with is a plan. And so it's wanting to do scenario visualization. So it's going to create comprehensive visualizations of workflow demand over time, cost versus reliability trade-offs, capacity mix comparisons, and so on. Then it's going to build an optimization to search through the different mixes of different types of instances that you could build and use in the particular optimization that you're running. And then it's going to generate some synthetic data, and it's going to model the capacity. So it's in the process of doing that. And if we're lucky here, we'll see some errors get created. So the agent is really good at writing code, but from time to time, you'll see one of these blocks turn red. And that'll kind of illustrate what is happening when the code iterates. So if, say, the code references a variable that hasn't been created yet, or it references a package that hasn't been installed, then the agent can go in and it'll see that, and it will iteratively try and fix the code in order to make it run. Now, on the left side of the screen over here, it looks very sort of notebook-esque, right? This should be very similar to like a Jupyter or something like that. Only there are some pretty significant architectural differences between what's going on in, say, a Jupyter notebook and what's going on inside what you see here. So in a Jupyter notebook, which is probably the most common data science tool that's out there today, those were originally invented at Berkeley, I think, about 20 years ago, to be classroom scratch pads, basically. And so if you'd run a cell like in this notebook, and it would create a global variable space. So all your variable values would be held in memory. And so then they'd be accessible when you ran more code. So when you execute more code, then that code would execute, and it would be able to interact with your previously created variables, but all held within that global variable space on your computer. So most Jupyter notebooks run locally. And so you would have the problem of, okay, your browser crashed. Well, now you have to rerun all your code. Or, oops, I ran my cells out of order. And so now my variables are in a bad state and I have to restart my kernel and then rerun everything in the right order to get everything to work. Well, something very different is happening here inside of Zerve. So you can see each cell on the left corresponds to a block over here in this DAG on the right. And so when this cell executes, so this is a cell that's generating synthetic data, and you can see that we're starting, it picks a random seed, and it's got a start time, and it's producing an hourly bit of data, like hourly workflow simulation. And you can see for each hour, it's looking at time of day and so on, and then it's generating the amount of workload that was created, and so on. Well, once this code executes, you have all these variables that were created, and I can have a look at these variables and visualize them and see what's what. So I've got a variable preview that's going on here on the bottom of the page. But instead of these variables being held in global variable space, instead they're serialized. They're cached and serialized and stored on disk. And then every block that's downstream of this block inherits those variables and gets to use them as they are. So if say this block, which is connected to this one, were to use the variable called demand and make these variables in this block would go unchanged. So every block represents its own kernel and maintains its own state. And so because the structure of the DAG is like that, your code becomes incredibly reliable and repeatable. And so code that you write here is no longer in a scratchpad type setup. It's in a very reliable, robust data pipeline that can be run many, many times in many different orders in many different ways. And that will be robust to what's going on. So you always get the same results every time. So this block is passing down its data to subsequent blocks so that they can be used in those blocks. Now it's a bit of a different workflow than like a notebook or something like that, because you have this ability to fork. And so when this block executes, for example, it's spinning up serverless compute and it's executing that compute serverlessly. So it'll basically start with all of its inheritances, which in this case there are none. It'll spin up compute. In this case, we're using lambdas in AWS, and it will execute this code. And the variable space at the time of that code execution will be, once it's complete, will be serialized and cached and stored on disk. That way, when I share this project with someone else, they could come in and they could see those results and see those variable values without actually having to run the code themselves. You know that in a Jupyter notebook, say, whenever I send that notebook to somebody, they have the monumental task of trying to get that notebook to run in their environment. So they have to set up exactly the same file system with exactly the same dependencies and put everything exactly where it's supposed to be. And maybe if they're lucky, the code will run, but they definitely have to run it in order to be able to access those variable values and start to work with the notebook that you sent them. Here, it's very different. It's a Google Docs type experience. And so you can all get in there, all work with the code. And notably, you can run as many blocks simultaneously as you want. Since they're all independent and they're all inheriting from upstream and they don't share a global variable space, you can run as many blocks as you want simultaneously. And so that gives you great opportunities for parallelization and also for collaboration when you're working together. So let's have a look at what the agent came up with. Let me jump back to see the comments here. Wow, okay, we've got a lot of comments. PK says, Greg, can you say anything about the data size limits for cloud computes and general security issues your clients might have suggested? That's a great question. So size limits, let me jump back here. Every one of these guys, you have the ability to select your own compute for each block. And so let's say I wanted to use lambdas or say Fargate containers, and I want, a really large container. So 16 cores with 120 gigs of RAM. I can select whatever compute that I need. Maybe I want GPUs, so I can go out here to a really large GPU image, and I can activate that and utilize that for my individual block. So previously, if I was trying to run my load on, say, like an AWS, and I'm trying to spin up a server to execute my code, I've got to pick the biggest server that I can in order to run whatever job it is. So I'm sizing for the most complex task in my workflow. Whereas here, each block can use different compute. So this block might need GPUs, whereas this one only needs a really small Lambda. And so I can surgically pick out which one is which. Now, you asked about security. This is running in the cloud. It's running in our cloud environment at the moment, but it was designed to be self-hosted. So it's about a 6-minute install to self-host this thing on AWS. We can install it on Kubernetes on any of the cloud providers. So it's a super easy self-hosted install. Zerve operates a control plane that handles orchestration, but all the data and all the compute lives in your VPC. So from a security perspective, if you have sensitive data, if you have things that you need to keep inside of your walled garden, as it were, then that is completely possible as well. There's also an air-gapped solution. So if a fully on-prem, fully hosted solution where the control plane lives inside the user's cloud environment, that's also an option. But that's really for the kind of the most secure, most sensitive types of operations. So hopefully that answers your question. And then also, does Zerve have a subscription model for model uses? I'm not sure that I understand that question exactly, but you can see on our website how the subscription model works. It's a free to use type approach. So you get 50 free credits every year. There is a pro tier if you need more credits. And then there are teams plans for like pooled credits for groups of people that are working together. So for teams and organizations and stuff like that. That way you can pool your credits and you can kind of work in a coordinated way, pool billing and stuff like that. But most everybody, well, a majority of people that use Zerve uses the free version, and we give a healthy amount of credits. So everybody should be able to, use Zerve productively on an ongoing way. So like, for example, this workflow, this entire project used 15 credits, and with the free plan, you get 50 per month. So you'd be able to do this project and probably 3 or 4 more on a monthly basis on our free tier. Of course, the pro tier gets 250 credits, and you can buy add-ons and stuff like that. So there's stuff like that. But anyway, we try to make a useful free product. Let's see. Any more questions? Okay, Paula says very interesting. Thank you, Paula. That's awesome. Okay, let's look and see what the agent came up with here. So at the end of the process, it always tries to summarize the analysis that it's done. And so for the data, well, first let's look at the visualizations. So the first one it came up with is a capacity type cost comparison. So it's comparing on-demand reserved and spot instances along with spot with retry overhead. So these are, of course, are linear because it's a linear consumption cost. So this chart is not particularly interesting, but way to go, agent, for giving that one a try. On-demand distribution with statistical markers. So this is actually the workload that was simulated with synthetic data. So this is the simulated workload for demand, and this I think is probably on a daily basis, but we'll see. Then we've got capacity type reliability comparison. So spot reliability is lower, and then reserved and on demand are, of course, at 100%. So those are there. And then these are different policies. So these are the 5 different scenarios that it looks like it generated. It looks like there were a lot more. It's just because this is number 29, number 70, number 37, and it's got a balanced one here as the one that it picked out. So that's interesting. And let's see, that was number 63. So here's number 63. And so it looks like a balance for this particular workload that was simulated is mostly reserved instances. with some on demand and some spot instances. So that's interesting. And then we've got cost versus reliability. So here are different approaches, and some with better reliability than others. Cost savings versus pure on demand baseline. So if you just bought only on demand instances, then you could save 36%, 30% based on different policies. So that's interesting. It looks like the workload demand over time is super seasonal. I imagine these are like daily demands, and that they spike during the middle of the day and then come down and are low at nighttime. So this is the demand. You can see it's a little bit spiky, which is interesting. And so we've got this guy is the one that we actually ended up, or that it actually ended up recommending. So this is the one with the balanced view, which is interesting. Capacity mix comparison. So this is costs per month based on which approach you take. And then exceeding capacity. So these are cases where you have to, I suppose, buy spot instances because your capacity was exceeded. One of the things I think that would be really interesting, and maybe we'll try this, is to see if we can generate much more volatile workload here. So here's kind of a summary of what it found with some key insights, and that's really fascinating. Let's try, can you make the volatility in the workload 100x more variable? And then rerun the simulation and show the effect on the recommended balance. Okay, so we'll see what it does there. That'll be interesting to make it much, much more volatile, because typically that would be a much harder problem to try and do rather than a very sort of normal, well-behaved kind of workload distribution. So we'll see what's going on here. Now, this is a kind of a toy problem, I suppose, because we're working with synthetic data, and the data that gets generated is typically going to be very clean. And so if you had your own kind of real data for a problem like this, I imagine that it would start with either the file system, so you could drag in a CSV file to compare or to get started, right? And the agent has access to the file system and it can see the data. Or you could connect to like a BigQuery or a Snowflake or something like that in terms of actually accessing the data in a database. So lots of ways to connect to your data. And of course, the agent can see all of that. So you don't have to spend time telling it, hey, the name of the file is this, and these are the variable names, and this is what each one means, and so on. The agent can see those things. And that's one of the big benefits of having a coding agent that actually lives in the environment where the execution happens, which is the big gap between most coding agents and working with data. So like a like a Windsurf or a Replit or a Cursor or some of these coding agents that are really, really amazing for software engineering, those are not so great for data, because data analysis and modeling tends to be a very iterative type process. And so, whereas with a Cursor, if you're building a web application, say, or an iPhone app or whatever it might be, that's kind of a fixed target, and you kind of know what you're going at, and maybe you want to like review it along the way. But with data, oftentimes step B is determined by what step A was. And so having to kind of like consistently iterate and point out what are the important bits of context and all that kind of thing can be really challenging. And so having the agent baked into the actual development environment is an incredibly helpful thing to be able to do. So this is the file system here. You can search for stuff. We'll go there. I did want to point out about environments here. So one of the things that you're often going to need to do in the case of building your projects is you're going to need custom dependencies. And so here we've got a number of builds of Docker containers built up, maybe one for computer vision, one for geospatial, say, lots and lots of deep learning ones and so on. You can create your own custom environments here that have your own packages, and those are reusable across projects. So let's say I wanted to do, train a neural network, and I need some specific packages along the way, and I've got these particular visualizations I want to use, or this idiosyncratic package that lives out on GitHub somewhere. Like, I can incorporate all that stuff into my project and then build those environments and have those accessible, not just to me, but to everyone else that's sharing my project. And I can share these environments with the folks that I'm working with on my team. So I have really good ability to customize my environment, both in Python and R. I suppose I should also point out here that because of the way we serialize the data, so after the execution of this block, say, um, all of these variables are serialized. And so, like, if, for example, if I had a data frame, a pandas data frame in this Python block, that would get serialized as a Parquet file. And it turns out that R knows how to deal with Parquet and SQL knows how to deal with Parquet. So within the same project, I can connect R blocks to Python blocks and interact with all the same data frames. So it's actually really useful for being able to work with mixed skill teams, right? Maybe you have some old school statistician folks that only code in R, but you've also got some more machine learning engineer folks that are in Python and some data engineers that are working in SQL. Well, they can all work together in the same project without having some code in RStudio and some code in, I don't know, DBT or wherever, and not, and some code in script files that live on their laptop and so on. All of it can be in the same environment, and you can do things like SQL query a pandas data frame, or use R to interact with the pandas data frame, so you treat it as if it were a R tibble, or like, all these things are interactive because of the way we do serializations here. So every time I click execute on a block, its first step is to deserialize the blocks, that the data from the blocks that are feeding it. And so we do that in a clever way so that you can interactively use R, SQL, and Python in the same environment. And incidentally, all of that syncs to GitHub. So if you use Bitbucket or GitHub or any of the online source control repositories, you can create branches and handle pull requests and manage your code there. And so those can interact with your tests and so on. Oh, you'll notice here, look, that was just an error. And so watch this block down here at the bottom right, and let's see if it can turn it green by editing the code to kind of like debug the problem. So that'll be something to watch in the background here. But you do have the ability to interact with source control and so on in order to make that stuff work. So let me jump back over while it's thinking here and look at some more questions. Do you have sample files you can share? PK, what kind of files did you have in mind? One of the interesting things that you can do here, let me jump to the other here. So if I just open a new window back on our site, there's a bunch of example data sets that are built into Zerve. So like, if you wanted to use Titanic, you could, this is the famous Kaggle Titanic data set that can get you started. This gets you started by reading that file into memory and kind of like displaying some of the details about it and so on. And so like, when I run this guy, that's going to automatically load this guy into memory, and I can kind of see, what's in the Titanic data frame. And let me close some of this stuff so I can see a bit what's happening here. And so this is that, did the person survive or not? And what are the details of that particular passenger? And so there are a bunch of data frames that are built into Zerve. And so, feel free to go in and use those as sample data frames to, to kickstart your work if you want to go in and kind of kick the tires and see what this thing does. So that's a good thing to be able to do. All right, and I heard the beep here that we're done here. Okay, perfect. Here's the critical analysis for your 100x volatility test. So your cloud cost optimization simulator shows a fascinating and counterintuitive result. Extreme volatility changes the scale of infrastructure needed, but not the optimal capacity mix strategy. Fascinating. Well, let's have a look here. Here is our demand, our new demand. Let me get zoomed in here. And so you can see there's some really huge peaks in terms of how much use is actually required over time, which is fascinating. But it's still saying that the same kind of distribution of on-demand versus reserve versus spot is producing the same basic cost, even though the total overall cost is much higher, which is fascinating. So that would definitely prompt me to want to kind of dig in a bit and see, exactly what kind of assumptions are going into this, exactly what kind of cost assumptions and availability and reliability assumptions were involved here. So let me kind of shrink this down and have a look a bit. So you can see some summary statistics here about the balance strategy and high volatility, cost and capacity requirements explode. Okay, so it's significantly more expensive if you have a very volatile workflow. That's fascinating, I suppose. But in any case, the point here was to illustrate that using these agentic coding environments, you can get a really fast start and a really strong jump on just how exactly the problem should be framed. And so for any particular use case, for any type of particular cloud load that your organization might happen to have, bits and pieces of this approach might need to be changed, and different optimization approaches might need to be taken, and different approaches might need to be had. But certainly by looking at these kind of plots and seeing how things shake out and what everything looks like, it's going to give you a really good insight into how to tackle this problem and what are the things that you may not have thought of that are going to be relevant to the particular circumstance that you're looking at. And so, depending on where's my agent button? Here we go. So down here at the bottom, it's proposing some additional next steps. So optimize for specific business requirements. So this might be if you have very high reliability needs. We can change the pricing models. So maybe spot instances are more expensive or less expensive. That's certainly going to change the reliability. Maybe you'd want to upload historical compute costs because they are variable over time, and you'll want to kind of compare those. Right now, I think it's using constant compute costs, and so that's probably a good next step to take here on this analysis. And then analyze how cost increases with reliability targets. So we looked at how volatility in terms of how much workload there is might impact how that might impact your optimization. But what if you had to be more reliable, or what if reliability was less important? What if it was more of a if it's there, we can do it. If it's down, it's not a big deal kind of situation. If it's maybe an experimental type group or workload that's not mission critical. And maybe cost is more important than reliability in those cases. So you could definitely kind of do a trade-off analysis between, what does it cost me to go from 95% reliability to 97% reliability? And then you can start to say, well, is it worth it to me? And so on. So anyway, that's kind of the approach that I wanted to take here. I'd like to take a minute and open it up to questions and see what things people are thinking about in terms of agentic coding. I would love to hear in the comments what kinds of agentic coding environments you folks have worked with, because one of the great things about ODSC is that it's a community of practitioners, and so nearly everybody that's involved that I meet with that's involved with ODSC is a data scientist of one stripe or another that's doing really interesting coding projects and trying out all the latest tools. And so I'd love to hear what environments you're using and what coding environments have been most impacted by large language models, and whether or not you think that coding agents are a useful tool to go into the kit of data scientists. So, okay, here we go. Visual Studio plus VS Code plus Claude, or VS Code plus Open Code Cursor. Okay, PK, that's good insight. PK, do you find that there is an overhead there in terms of having to teach the models what your context is for your data? Like, I have not had good success trying to interact with like Claude and Cursor and those when I actually had a data set that I was trying, or multiple data sets that I was trying to work with. That seems to be a major hurdle with those environments, is getting that environment and copy pasting, and then execution. Like VS Code is great, but it runs pretty much locally, and like there's a lot of setup there and stuff like that. Do you find those to be okay? Yeah, there's a lot of teaching needed in KPK, but I'm super thrilled to have been here to be able to talk to you guys and show you what we've been building at Zerve and show you how I think that coding agents are impacting the way that data scientists do their job. Michael Bowen says, I use Warp and I'm learning temporal. I've done a lot of context stuff for longer prompts. I'm code first. Okay. Uh, so longer prompts, I'm actually really interested in what you mean by that, Michael, because I've done some experimenting around whether or not it's good to send a super long prompt, like put in every possible detail and make it super, super complicated and, like try to give full context in a prompt. I've seen guys spend 45 minutes or an hour writing a prompt to go and get the coding agent to build what you want it to build. But then at the same time, I've seen folks put in a couple of sentences like I did here, and then iterate a few times and get an even better result. So I tend to be in the camp that says that smaller prompts are much better than bigger prompts, and that it's probably not worth the time investment for writing those big, long, complicated, complete prompts as it is to just try and one shot it and then iterate as you need to. Michael says I'm now breaking them out as XML like because I want to do more specific agentic control. Yeah, I think Michael, I think that is the next kind of like frontier for these agents is being able to control them. So, like for example, if I wanted to go in and change everything or give kind of global access, I would interact with the agent here. But if I wanted to be a little more targeted, then I could go in here and say, oops, let me hide that. And I could say, all right, I don't understand this code. Can you add more comments? And so when I do that, what I'll see is that the agent is receiving all the same context still, but now its ability to change the code is limited to just this block. And so I've only asked it to add comments here. But what you'll see is the agent's going to go through and it's going to try and add some comments in, and it'll show me the diff between what it wants to make the code say and what the code actually says. And so you can see here we're deleting this bit and we're replacing it here. And so I'll just accept these changes, and you can see, sure enough, okay, here's a bit more code. But it hasn't had access to the other parts of the project, and it hasn't had the ability to go in and change other things. So I have some control. And if I were to select a specific bit of text, I can control, exactly what the agent sees and exactly what the agent has access to change in a really fine-toothed kind of surgical type way. And that's really important to being able to trust that the agent isn't going to foobar your project. Whereas, if I go down here on the right side and I say, okay, make this change, then, the agent has full reign there. So having that very detailed control over what you're doing is really important when you're working with an agent. Let's see. PK, great for prototyping, not sure for operationalizing. Well, let me show you something. So there's a couple of really interesting things you can do in the deploy space here that might be of interest to you. So you can deploy as an API. It's very straightforward, and the agent can certainly help with that. So say you train a random forest and you want to build an API that returns predictions from that random forest. That's a really fun and easy way to deploy your models. You can build Streamlit apps that are interactive, and you can ask the agent to build them for you that rely on the code that you've written in your backend. And you can do some more custom stuff. You can schedule your code to run. So like if I wanted to go in and have this thing run every day at 5 a.m. before I got into work, that would be one thing that you can do. So you have some scheduling opportunities here. And then one feature that we'll be releasing very soon in beta is called reports. And that's going to give you a way to build a an application, an interactive application that surfaces some of the details that you found in your analysis here that you can share with folks. And so you can host it you can supply a URL and it will make that where you can send it to folks. And so you can deploy your results as a report, and the agent can help you build that report out without you having to know, how to build those applications and so on. So lots of interesting things that you can do in the deployment and operationalization space. And so, of course, notifications are built in and source control and all that kind of thing. So we've really tried to make it where the application supports not just prototyping, but also the ability to kind of deploy these things in a broader context. Let's see. Michael says a lot of folks don't talk about token budgets. Right now, large language models don't have the equivalent of query planners, so all the memory chunking is imprecise. The memory management session by Qdrant was instructive over loops. Token budgets, that's interesting. So, there's a couple of ways to think about it, I guess. I think what you're getting at is the size of the context that you're passing to the model. Because a lot of times, the way that your queries, your prompts start to cost more money is when your context window starts to get bigger and bigger. And so if you have a huge amount of information that you're trying to pass to the large language model, you might be limited in terms of what is the context window, maximum context window size, but you're also limited in terms of how much you want to spend on these actual queries. So we've got some organizational controls that are built in there around like, okay, how much can things cost, and what are the limitations there. But you've also got controls in terms of being able to monitor what people are using and so on. So there's some interesting things going on there. PK says, Greg, how easy is it to debug the decision tree? Well, it's a good question. So let's go in and create some bugs and see what we can see. So here's our decision tree. It's pretty simple here. You can see what's connected to what and so on. And for each cell, you can see what the inputs are. So like if I go to this variable, this particular block, I can see what it's inheriting from upstream. And so I get a sense for what goes where. Let's say I go to this guy and I'll just put in a semicolon. Maybe it's just a simple typo, something like that. That will definitely create errors. And so you'll notice a couple things happen. One is the stuff downstream turned from green to purple, which is pending. So these blocks here that are downstream and dependent on this block, they know that something happened upstream that means that they don't have the latest for what's going on. And so the color kind of gives you a sign of what it is that you need to do in order to make sure that each block has the latest. And so the nice thing about the agent that you're working with here is that you can have multiple conversations going on at the same time. So this is the one we started with. This is the one that I just started when I said open error assist. And so we'll see what it does here. Let's go find that semicolon that I added. So there it is, line 27. And so we asked it, hey, can you find the problem? Now, this is silly, right? Like it's definitely going to be able to find that semicolon and fix it. There's no question of that. But the point is that it's real easy to kind of kick off these debugging type things in terms of letting the LLM look and see what's going on. And so it does have pretty cool debugging capabilities in terms of, oh, and there it goes. It took that away and fixed it, and now it's executed, and there it is again. And so now I can rerun these 3 blocks. And I know that I don't need to, but still they don't. So because this code executed, these guys need to be turned green again. So there is pretty capable large language model integrated debugging built in here. And you can change any of these relationships here, right? So like if I cut off this block, it would hop down to the beginning here and it would no longer be connected. And so if I ran it, it wouldn't have those dependencies that it needed. And so you can change the connections that are built into your graph and kind of monkey with how things are connected and so on. So you have control over that as well. PK, Michael, token sizes are embellished by context sizes, access to different types of memory, I guess. Yeah, that's fair. Michael says, I only seen one tool since day one where there was a tool that tracked large LM context memory usage. Yeah, that's fair, I suppose. I suppose you're right. That might be an interesting thing to look at. So yeah, that's a good piece of context. Michael, thank you. I hope Zerve has a future too. And I encourage everyone to get in there, kick the tires, send me some feedback. It's just Greg at Zerve.ai. You can shoot me a note. I'd be glad to hear your thoughts and comments. We've got a Slack community, so you can log in. I want to see your projects. We've got a gallery where you can publish your work to the gallery and share it with the community. Lots of cool things going on there, and lots more really cool things to come. So thank you all for tuning in, and I am going to call it to a close and set everybody free. So I really appreciate your time. Thank you all very much.